Okay, so let's talk about the topics that'll be on exam 3. So this is going to cover only open channel flow. There won't be any material on pipes or pipe networks or pumps, although our general material we've covered on the energy equation, mass balances, force balances could potentially apply. So here are the topics that are going to be most relevant for you. First, you're going to want to know how to compute hydraulic geometries. As a function of depth in the channel. So this would mean things like the cross-sectional area, wetted perimeter, hydraulic radius, and top width. You're going to want to understand uniform flow, what it is, what characterizes it. You're going to want to know how to compute the discharge in an open channel, given the depth, using Manning's equation. You're going to want to know how to compute the normal depth for a given discharge. So remember, the normal depth refers to the depth achieved under uniform flow conditions. So you're going to want to know how to compute the normal depth given a discharge. And you're going to want to know how to analyze uniform flow for both prismatic and irregular channels. So know how to apply Manning's equation, not just for a regular shape, but also potentially for compound channels consisting of multiple parts. Are there any questions on these topics so far? All right, the next set of topics correspond to energy principles applied to open channel flow. So you're going to want to know how to compute the critical depth for flow in an open channel. You're going to want to know how to use the Froude number to characterize flow or classify flow as subcritical, supercritical, or potentially critical flow. You're going to want to understand the general concepts of sub and supercritical flow and what they mean. So that could potentially mean understanding how the speed of a small gravity wave relates to the speed of the bulk velocity of water for sub and supercritical flow. And you're going to want to understand how to draw and analyze specific energy curves. Next set of topics correspond to gradual transitions in flow. So these refer to things like changes in the bottom elevation, changes in the channel geometry, and how the flow adjusts to those changes. So you're going to want to know how to apply the energy equation. to compute changes in the water depth and velocity due to changes in the channel geometry. So that might mean constrictions in the width or expansions in the width. And changes in the bottom elevation. So that might mean a bump or a dip in the bottom elevation of the channel. So understand how you can apply the energy equation and the concepts of specific energy to understand how the water is going to adjust to those transitions. Are there any questions so far on these topics? All right, next set of topics, hydraulic jumps. So you're going to want to understand how to compute the sequent depth downstream of a hydraulic jump, given the upstream depth and velocity. And this may apply to a rectangular or non-rectangular channel. You're going to want to know how to compute the sequent depth under the presence of energy dissipators. So compute the sequent depth with energy dissipators. And you're going to want to know how to compute the energy losses through a hydraulic jump. The next topic is weirs. So for this topic, we're going to focus just on broad-crested weirs. So know how to compute the discharge for an ideal broad-crested weir. Understand the assumptions that go into deriving the discharge equation for a broad-crested weir and how they might be adjusted for certain other conditions. Okay, are there any questions on these two subjects related to rapidly varied flow? All right, and our final set of subjects correspond to gradually varied flow. So what we talked about last time in class. So you're going to want to know how to compute the water surface profile for subcritical flow and supercritical flow. And you're going to want to know how to compute this water surface profile using or by applying an explicit scheme. So this is the forward Euler scheme. And what we're going to be covering today, you're going to also want to know how to apply an implicit scheme as well. So I'll talk about why you might want to do this. So this is also known as backward Euler. Again, a useful skill to have, not just for hydraulics, but for civil engineering and engineering in general. So these are the topics that are going to be on the exam. So remember, this is a take-home exam. I'll release it at the end of class on Tuesday. Because it's a take-home exam, it will be a bit harder than an in-class exam. So I will ask questions that will probably challenge you, questions that don't directly correspond to any particular homework problem or problem that we've done in class. So I do want you to think about these problems. So keep that in mind. Are there any questions about the topics that will be on the exam? Any questions about the logistics of the exam? All good? All right. Well, let's go ahead then and get back to our final topic of the class, which is gradually varied flow. So last time we introduced the concept of gradually varied flow. So can anyone remind me how gradually varied flow is defined or how it differs from uniform flow? So how is gradually varied flow different from uniform flow? Yes?
Depth and velocity of flow vary along the
Very good. So for gradually varied flow, the depth and velocity of flow will vary along the length of the channel. Typically, as the name implies, it will do so gradually. So the slope of the water surface will generally be much less than 1. So we derived an expression for how we can compute the water surface profile under gradually varied flow. We arrived at this expression by using our mass and momentum equations, and we came up with this differential equation that describes the water surface profile. So this term here, this represents the slope of the water surface. S naught, this is the bottom slope, so the slope of the bottom of the channel. SF is the friction slope. And this term here is the Froude number squared. So we arrived at a differential equation that we can use to explicitly compute that water surface profile, given some set of boundary conditions. We also showed that we can estimate the frictional losses needed to compute this water surface profile using Manning's equation. Essentially, just by rearranging Manning's equation, we can compute this frictional loss term. So how do we actually go about computing the gradually varied flow profile? Well, we can't solve it analytically except for in very simple cases. Instead, what we proposed is a numerical method of solving this problem based on discretization. So we break up our channel into a bunch of little chunks. We start at some boundary, and then we use this following recurrence relation to compute the depth of water at each spatial increment along the channel. So this equation was obtained just from discretizing our original differential equation for the gradually varied flow profile. And then we can apply this recurrence relation to just essentially step through the channel and compute the depth at each spatial increment. So let's say we start with a channel. The way that we progress depends on whether we have subcritical or supercritical flow. So if we have supercritical flow, we start at the upstream end of the channel. If we have subcritical flow, we start at the downstream end of the channel. And we break our channel up into little chunks. And we start at some boundary where we know what the depth is. So let's say we have supercritical flow. We can start at the upstream boundary. We know what the depth is. So we plug that depth into our equation here. So that becomes this HK. And then we can compute the next depth in sequence, which will be H1. So we apply this process and we just step forward through the channel, applying this same rule at each spatial step. For subcritical flow, it's the same, except in the reverse direction. We start at the downstream boundary. We plug that downstream depth into our recurrence relation to compute the next depth upstream. And then we just proceed stepping through the channel, essentially until we arrive at the end of our domain. So from our problems last time, you noticed that the depth converged to a particular value. What was that? What was the value that the depth converged to in our channel? Sorry? So when we had a backwater, as we proceeded upstream, that depth in the channel converged to a particular value. What value did it converge to? Not unless there is some kind of transition or something that would cause a transition upstream. So it's the depth that is achieved over a channel when the slope is relatively constant over a long distance. The normal depth, right? So the depth will eventually converge to the normal depth as we move in the upstream direction for subcritical flow. It'll converge to the normal depth as we move downstream under the case of supercritical flow. So I gave you a problem to work on last time. We looked at computing the backwater profile of a imposed by a dam. So I gave you this problem to work on. We went through how we could solve this in Excel, and I give you a few problems to solve based on that Excel spreadsheet. So what I'm going to do is for the next 10 to 15 or so minutes, I'm going to let you work on this problem and finish it up. And then I'm going to show you another way of solving this problem that is required under certain conditions. All right, so in the interest of time, I'm going to move on. So you can have, I'll give you some more time later on in class that you can work on this problem and the next problem that I'm going to be talking about. But I am going to move on for now. This in-class assignment is due at midnight tonight, so just make sure you get that submitted. Okay, so let's look at another problem. So we looked at backwater imposed by a dam. So we looked at a subcritical example of gradually varied flow. Let's take a look at a problem involving supercritical flow. And specifically, I'm going to look at a problem that's similar to one of the homework problems you looked at on homework 7. So we have a rough trapezoidal channel. The problem statement, by the way, is up on Canvas, so you don't have to write this whole thing out. It's under quizzes, in-class gradually varied flow, supercritical. But we have a rough trapezoidal concrete channel with a 3.5 foot bottom width, side slopes 2 to 1 horizontal to vertical with a bottom slope of 0.012. So that's pretty steep. And it discharges 185 cubic feet per second of water from a reservoir. So like the problem you saw in homework 7, the critical depth is achieved at the channel entrance. So this is a pretty common condition that happens when you have a reservoir discharging into a steep channel. Your job is to compute the water surface profile for this case. So we have a reservoir. It is draining into a steep channel. There is some water surface elevation in the reservoir. And then at the channel entrance, we have that the water achieves the critical depth. And then it's going to go down and obtain supercritical flow on the steep channel. And eventually it's going to converge to the normal depth. So we have critical flow achieved right at the entrance of the channel. And we achieve the normal depth at some point far downstream. So what we want to do is we want to compute this water surface profile from the mouth of the channel, stepping downstream using our gradually varied flow equation. So we have H naught corresponding to the critical depth. We want to proceed to H1, the next step downstream, and so on and so on. So let's go ahead and try to apply our same recurrence relation we used last time. So we have that the depth at the next spatial step is equal to the depth at the current spatial step plus this term here, where the friction slope and the Froude number are evaluated at the current spatial step. So let's start at H0, the point where the critical depth is achieved at the upstream end. And we will get something like H1 is equal to H0 plus delta X times quantity S0 minus SF evaluated at a critical depth, H0, divided by 1 minus the Froude number squared evaluated at H0. So what's one potential problem you might see with this approach? What is our boundary condition at the upstream end of the channel? Critical depth. Why is that a problem here? That is correct. So if we apply this technique naively, the Froude number here evaluated at the critical depth, this will be equal to 1. So the Froude number squared will also be equal to 1. Therefore, this denominator will go to 0, and this term here will be undefined. So our explicit method won't work. So thinking back to computer methods, are there other techniques that you learned for numerically solving differential equations that might help here? So we I showed you an explicit method here, or the forward Euler method. Are there any other techniques you used for solving differential equations that might be useful? Maybe just thinking to our schematic here, how might we go about changing this method to eliminate this problem? Oh, yes.
Yes, but it's the backwards one. It seems like we should start at the other end and work our way out. So subtracting from like one end and moving to the direction.
So you're on the right track. So the backwards, there's another method for solving differential equations. So backward Euler. Backward Euler, let's talk about what it is. So it doesn't mean proceeding in the other direction, but what it means is that you'll use a different point to evaluate these functions. So with the forward Euler method, we used the depth at the current step. So let's say we start off at the top, at the upstream end of the channel. We evaluate this term using that H0 value. For an implicit method, instead of using the current value of the depth, we'll use the next value in sequence. So let's go ahead and apply this method. I'm going to just define it here. So we can apply an implicit method. This is also called sometimes backward Euler. And we'll define our recurrence relation as follows. We have that the depth at the next step in sequence is equal to the depth at the current step plus delta X times quantity bottom slope minus the friction slope. except that this time we're going to evaluate the friction slope at hk plus 1, i.e. the next depth in sequence. Similarly, for the denominator, we have 1 minus the Froude number squared evaluated at hk plus 1, the next depth in sequence. So what's one thing that's more potentially complicated about this approach than the explicit method we just talked about before? It has to be computed iteratively. Is that what you're going to say? Right. So we don't know what hk plus 1 is. So evaluating this function here for the friction slope and for the Froude number, this has to be done iteratively. So we're going to apply kind of the same technique we've been doing all along in this class. We're going to solve iteratively at each step. So we will take, we'll be wanting to set our equation that we're interested in solving to 0. And what we're going to do is we're going to take a trial value, hk plus 1. I'll call this hk plus 1 star. And we're going to subtract our computed value for hk plus 1. So that'll be hk minus delta x times quantity, bottom slope minus the friction slope evaluated at our trial value of hk plus 1 star divided by 1 minus the Froude number squared evaluated at our trial value of hk plus 1. And we iterate at each step until convergence. So it's similar to the explicit method, except that at each spatial step, we solve this equation iteratively for the depth hk plus 1 at the next step in sequence. Yes?
Sorry, what is the star indicate?
It indicates that this is our trial solution. So it will converge to the actual solution. So this is our trial solution. So yeah, at convergence, this term here will equal this term. So let's go ahead and try this out. I'm going to walk you through how we can apply this to this example problem I showed. So remember, the problem statement is up here under Canvas quizzes. I've also uploaded a spreadsheet under Canvas files, lecture 23. Should be here. Under Canvas files, lecture 23, there should be a file, an Excel file called supercritical implicit method. Is anyone able to download this? Can I get some hands just to show me? Yes, okay, thank you. So under Canvas files, lecture notes, it should be there. I don't know why it's not loading for me. Oh, there we go. So go ahead and download that spreadsheet. It's this one right here. And I will open it up on my computer here. So let me just quickly run down what the different entries in this spreadsheet mean. So on the left, we have our parameters that apply to the entire channel. So we have here M, our side slopes, which are 2 to 1. Discharge is 185 cubic feet per second. Bottom slope is 0.012. Roughness is 0.022. Here's the bottom width of our trapezoid. Just ignore this H naught for now. dx, this is our spatial step size, and then g is the acceleration due to gravity, and phi, because we're in US units, is going to be 1.49. So our columns, x, just like the previous spreadsheet, is our spatial coordinate along the channel. This time we're moving in the positive direction because we're going downstream. H, I'll get back to this, but this is going to be our depths. Right now, this is just filled with dummy values. We are going to fill these in though. A, this is the cross-sectional area that's computed from that depth. P is the wetted perimeter computed from that depth. R is the hydraulic radius computed from that depth. T is the top width. SF is the friction slope. FR2 is the fluid number squared. Z is the bottom elevation of the channel, and water elev is the water elevation. So we want to compute all of the depths as we move down the channel. The first thing we need to do is we need to compute what our value is at the upstream end of the channel. So how can we do that? Note that all these 2.75s, these are just dummy values. These are made up. How can we compute the upstream boundary condition? Yes.
Can we use like root number equation to solve for H, the critical?
Very good. So we are going to solve for the critical depth, and that we can use as our first entry in the depth column. So I'm going to do that over here to the side. So I'm going to create a cell for the critical depth. For the fluid number, we're going to need the top width, and we're going to need the cross-sectional area. And then I'm going to have an equation that I am solving to set the fluid number equal to 1. So for the critical depth, I'm going to use an initial guess of 3 feet. The top width is going to be, for a trapezoidal channel, it will be the bottom width, that's B6, plus 2 times the side slopes, that's B2, times the depth, which will be B12. That's our critical depth that we're trying to solve for. For the cross-sectional area for a trapezoidal channel, this is going to be quantity bottom width, that's B6, plus side slopes, that's B2, times the critical depth, close bracket, all times the critical depth. And I'll paste this equation to the side. Okay, then for our objective here, we're going to try to set the fluid number equal to 1. I think it's easier to work with the fluid number squared, so that's what I'm going to do here. So I'm going to set the fluid number squared equal to 1. So I'm going to do 1 minus the... Oh, yes, go ahead and take a power strip. 1 minus the discharge cubed times the top width divided by the acceleration due to gravity. It's B9 divided by the cross-sectional area cubed. And I'll paste this to the side for you. And now we can solve for the critical depth using goal-seek or solver. I'm going to use goal-seek. So I'm going to go to data, what if analysis, goal-seek. We're going to set cell B15 to value of, what should the value be? 0, because we're using 1 minus the fluid number squared. By changing cell, what cell do we want to change? HC, which is B12. Okay, let's go ahead and solve it. Oh my goodness, what happened there? I think I typed something in wrong. Oh, I see what it is. Can anyone else see where I'm in error? Where is it? It's in cell B15. Right. So the flow rate needs to be squared and not cubed. All right, let's go ahead and try this again. Okay, we're gonna set cell B15 to value of 0 by changing cell B12. And we get an answer about 2.761. So we can go and take that value and plug it in as our first depth. This will be 2.7615-ish. And you'll see that all of these cells here get their values adjusted. So 2.761 is the critical depth, and that is the first depth at the upstream end of the channel. All right, so the next thing we need to do is I'm going to set this value of our equation to 0 because we know that that is the correct depth. But for each of these subsequent rows, we need to solve this objective function. So we're going to take the depth at the next step minus the depth at the previous step minus this computed term here. And for each of those, we're going to iterate that row until convergence to solve for the depth. So let's go ahead and do that. Okay, so for this first row here, we want H at this step. So that's going to be cell E3 minus H at the previous step. So that's cell E2 minus the spatial step size. So that's going to be quantity. Well, it's going to be 10 always, but you'll need this set up for the problems. So it's going to be cell D3 minus D2. So that is our delta X. If we want to change the step size, for instance, you might want it set up like this in your spreadsheet. Okay, so we have HK plus 1 minus HK minus the spatial step. And now we're just going to multiply by quantity bottom slope minus the friction slope. So our bottom slope is cell B4. I'm going to use an absolute cell reference there. Minus the friction slope. What cell will we want to use here? What cell will we want to use here? J, which J? J3. Remember, we're evaluating it at the current depth. So this is going to be J on the same row. And then we're going to divide by 1 minus the Froude number squared. So that's going to be K2. Oh, sorry, K3. So I'm going to go ahead and just double click this little bottom right corner to extend this formula to the rest of the cells. If that doesn't work for you, you can drag it down. I think there's only 32 entries here. And now what we need to do is we need to change the values of H. So that's column E until each of these equations is equal to 0. Now we could step through and solve each of these individually using goal-seek or solver, but that's kind of tedious. Is there a better way that we could solve all of these all at once? Yes. Sum squared, very good. So we can use the same technique that we use for pipe networks. So I'm going to create an objective here. And what I'm going to do is I'm going to take the sum of the squares, that's sum SQ, of N2 through N32, I believe. Yes. So sum square of N2 through N32. Okay, so that is our objective function. If this objective goes to 0, that means that all of these equations go to 0. So we can solve for all of these depths simultaneously. Yes. You mean in this equation? It's because this column here, this is the fruit number squared. It's already squared for you, yeah. Yes, to the left, these ones? Okay, so I'll give a minute to get these down and then, okay. Okay, so before we lose track, let me go ahead and finish this process. So we are going to make this objective function go to 0. To do that, I'm going to go to solver. We're going to set objective P2. We're going to minimize it. So we're minimizing that sum of squares by changing variable cells E3 to E32. So let me just go ahead and highlight these again. So this is cells E3 through E32. This should already be set up for you. And there's one more thing we need to do. So we need to impose constraints or else the solution will not converge. So I'm going to delete these and then put them back in. The first constraint we need is we need to make sure that all of the depths are supercritical, because there are 2 potential solutions to each one of these depths. We want to enforce that it's going to be supercritical. So we're going to make it such that cells E2 or E3 through 32 are less than or equal to 2.76-ish. I think it's 2.7615, but yeah, 2.7615. And then second, we're going to make sure that the depths are greater than 0. If it becomes negative, the solver will also not converge. So we're going to take these cells here, and we're going to make them greater than or equal to 0. And note that here, I'm only changing variable cells E3 through 32, not E2 through 32, because E2 is our boundary condition, so that we don't want to change. Okay, so hopefully I did everything right here. I'm going to go ahead and hit solve, and let's see what happens. Oh yeah, it should be O2. I think previously I created another column with all of the elements squared, so if it says P2 as your objective function, just set it to O2. So let's go ahead and hit solve. So it looks like the objective function is going. I'm not totally satisfied with this answer, so I'm going to run it again. Oh, there we go. Okay, so I got it down to 5 times 10 to the negative 5th, which is pretty good. So you can see here in our column E, this gives all of the depths. You can see it converges pretty quickly to about 2.4. Just before I let you go to work on this problem, there's a second sheet that shows the plots of the water surface profile and the water depth as you proceed downstream. So you can use these plots to visualize. So I'm going to give you the rest of class today to work on this in-class activity, where I'll also give you time on Tuesday, because I think we don't quite have enough time for you to finish this problem in class today. But I will come around to help as needed. I know that was fairly quick, so raise your hands if you weren't able to get everything. I'll come help, okay?